All right, Chris Good here, and this is a really quick lecture on the related samples or repeated measures t-test. So far, we have learned how to do the independent groups t-test and independent groups design. And independent groups is for when you have two groups. For the simplest comparison, you're comparing two groups of different people. So different people are treated differently. And we looked at an example of ginkgo where we had, one group of people was taking ginkgo and the other one was taking the placebo. But we actually could have done this as a repeated measures or within subjects design. The independent groups design is also often referred to as a between subjects design, even though we call human subjects, we call them participants, but we'd call this between subjects because we're looking for differences between two different groups of people. But we could also do a repeated measures design. We call it repeated measures because these are the same people under different conditions. They're tested multiple times, and that's why you're measuring them repeatedly. Under different conditions. Simplest case, you do it 2 times for 2 different conditions. Okay. We also call this the within subjects design because we're looking for differences under these different conditions within the same group of people. Okay, so how would we do this, and what's the appropriate statistic to use? Well, for the independent samples, we use this formula for t. It's the difference between 2 sample means, right, minus some, let me make that a little more clear, please, minus some hypothetical population mean difference, right, divided by our estimated standard error of the difference between those 2 sample means. Well, the t for the repeated measures test, the repeated measures t-test, which we also call the related samples, right, t-test, is actually much simpler. So t in this case, we're only looking at the value of one number, and that's something we call the mean difference score. So we do it like that. Now, in this formula, we have this hypothetical population parameter, just like in all t-tests. And we also have a hypothetical population here. If this, m sub d, we're going to call that the mean difference score, and I'll show you what that is in just a moment, then we're actually comparing it to the population mean difference score. And we write that like that. And guess what? We divide it by the estimated standard error of what? The mean difference score, S sub m sub d. I'm going to show you how to calculate all of those really quick. But we need some data, first of all. Let's imagine that we were doing the ginkgo study again, and we have our control condition, right? And we have 5 people in it, 5 scores. 2, 3, 5, 6, and 4. All right. So this is the placebo group. If we did this as an independent groups design, we'd have this other group that got the treatment, but we're actually going to use the same people. Now, there's a bunch of caveats, a bunch of warnings about using this type of method, especially when you're doing some kind of drug study like this, where you don't know if the effects of the drug are going to persist, and the order in which the same people experience these different conditions could really have an effect. So we got to talk about ways to control for these order effects that could be confounding. But we're going to do that in a separate lecture. I just want to show you how the statistic itself works first. Okay, so if we're using the same people, then for each participant, right, and I'm going to write just participant numbers down here, number 1, number 2, number 3, number 4, and number 5. We already have their memory score while they were taking the placebo. But for each person, they'll also have a score when they were under the ginkgo treatment. And here are their scores, 6, 7, and 5. Now, we could look at the means for these two groups, and we'll need to find out, on average, under what condition these same 5 participants performed better. But we want to find out if that difference is significant. And in order to do that, we need to calculate their difference score, right? Their difference score. We're going to do that by subtracting the treatment minus the placebo. And it doesn't matter which direction you subtract it as long as you're consistent. And you have to do it the same way for every participant. I'm just writing this down here so that I know that when I calculated the difference scores, I was subtracting the placebo from the treatment. So if we get a positive number, that means the treatment condition was better for that participant. Okay, so 4 minus 2 for this first one, that's 2. 4 minus 3 for the second one, that's 1. 6 minus 5 for the third one is 3. 7 minus 6. Sorry, 6 minus 5 is 1. 7 minus 6 is 1 for number 4. And then for number 5, 5 minus 4 is 1. So we actually had positive difference scores for each one of these participants. Well, what I'm really interested in is the average difference score. And you can write that two ways. Some textbooks write d bar. Some textbooks write m sub d. That's what we're going to use. And that's just the sum of the difference scores divided by the number of difference scores. We have 10 total scores here, but we only have 5 total difference scores. So if we sum all these up, that's like 6, right? 6. That's 2 plus 1 plus 1 plus 1 plus 1. Right? 6 divided by the number of different scores, which is 5, right? And that's going to equal 1.2. Oops. 6 divided by 5 is 1.2. Okay, so that's our mean difference score. And now, how are we going to use that in this repeated measures related samples within subjects T formula? Well, let's just walk through all of the null hypothesis testing, significance testing steps. And the first one is always going to be state that null hypothesis. For independence groups, it's this one, mean 1, population mean 1 minus population mean 2 is 0. So we had 2 samples that were taken from the same population, or rather populations with the same mean. But we're not going to use that for the null. Here, we're interested in this difference score, and we're relating the sample mean difference score to a population mean difference score, which if this treatment, right, control versus treatment, if the treatment really has no effect, what should the population mean difference score be? It should be 0, right? If the null is true, then, and the treatment doesn't do anything, on average in the population, the difference between your treatment score and your placebo score will be 0. This is going to come in handy when we use this formula. We'll be able to actually calculate T, because we're going to plug in this null hypothetical value. Okay. Step 2 is to look at your alpha, which we're going to say is 0.05, and determine what the critical value for T is. Now, if we had 2 groups of different people, we'd have a n of 5 here and another n of 5 here, which means 4 degrees of freedom here and 4 degrees of freedom here, which means when you pooled the degrees of freedom, we'd get 8. But we don't do that when the repeated measures test. We are interested in the number of different scores. So the number of different scores is equal to 5. Same thing that we used when we were calculating the average difference score. And so the degrees of freedom here are going to be 4. And if we go to our t table, right, we can look up what is the critical value of t at 4 degrees of freedom and an alpha of 0.05 and 2 tails. And it's 2.776 for 4 degrees of freedom. We're going to say plus or minus, right? Because we're doing 2 tails. And then all we have to do is calculate t. Well, t, once more, is your mean difference score minus some hypothetical population mean difference score, and that's what we're going to put in there, divided by the estimated standard error of the mean difference score. Let's take a look at that denominator. What is that? Well, it's going to look really familiar because the estimated standard error of the mean difference score is the square root of the variance for the different scores divided by the number of different scores. The variance of the different scores is the sum of the squared deviations of each different score from the mean difference score divided by your degrees of freedom. And the sum of squared deviations for the different scores is just the sum of each different score minus the mean difference score, and you square that difference. Let's do this for our data up here. 1.2 is our mean difference score. So for the first score, we do 2 minus 1.2, and we square that. 1 minus 1.2, square that. And do that for the rest of the scores that we have. We had 4 ones. All right. So let's get out our calculators. Now in Excel, this is going to be a lot easier for you guys, right? So that first one is 0.8 squared. And for all the rest of these, it's going to be 0.2 squared. All right. So 0.2 squared is actually 0.04. And 0.8 squared is 0.64. So 4 0.04s is 0.16. And if we add these together, we should get 0.8. Okay, that's the sum of the squared deviations of each one of these scores from the mean. So we'll just plug that in here to calculate our estimated standard, to do our variance, right? So 0.8 over 4 degrees of freedom is 0.2. And then we can plug that in up here, square root of 0.2 over the number of different scores, which is 5. All right, that's the square root of 0.04, which is 0.2. That's not a very good 2. Let me write that one more time. It's 0.2. Okay, now we can plug our estimated standard error of the mean difference scores into t and get t. Come on, let's write it correctly. T, that mean difference score minus the population mean difference score divided by the estimated standard error that we just calculated. That's our mean difference score of 1.2 minus our hypothetical population mean of 0 divided by 0.2. Well, 0.2 goes into 1.2 6 times. Right? That means that t is 6. So if we look, where's our critical region here? Well, it helps to draw it out. If we do the frequency distribution of t, which is, again is centered at 0, and we decided that our critical values were plus and minus 2.776. Right, shade in that critical region. All right, where is 6? Well, it's way out here. It's above 2.776. So our decision is to reject the null hypothesis and conclude that, well, how do we know which group performed better? Well, because we subtracted treatment minus placebo and we got an average positive number, it means that on average, participants had a higher score while they were taking the ginkgo, the treatment. So we can say that ginkgo significantly improves memory scores compared to placebo. With t at 4 degrees of freedom equal to 6, and p, well, what is p? We don't really know what proportion lies beyond 6, our observed t-value. But we do know that it's smaller than these two proportions combined, which was 0.05. So all we can really say at this point is p is less than 0.05. All right, and that is how you do the repeated measures within the subject's related samples t-test. We'll talk about problems with this design in a different lecture. I'll see you in class.